Hi all. In this section, we'll be looking at section 1.8, which is going to cover inverse functions. It's a pretty short but fun section to look at. So looking at the objectives here with you, we will first be able to verify inverse functions. Any function composed with its inverse is just going to lead back to x. So we'll look at some problems dealing with that. Find the inverse of a function. Use the horizontal line test to determine if a function has an inverse. Use a graph of a one-to-one function to graph the inverse function. And then finally, we'll find the inverse of a function and graph both functions on the same axes. I just got through working the homework assignment, and there's problems that deal with every single one of these objectives. After you get through watching this video, I hope you'll go ahead and try the homework. And again, as always, refer to my homework should you need any assistance. And after that, let me know if you need any assistance. First of all, when we define an inverse function is just something that's going to undo whatever the original function did. So when I plug x into the function g is going to do something to x. So it's going to change the value of it. Whatever it changes the value of, if I plug that new value into the function f must undo it and take it back to x if it's the inverse. That's what this is saying here. It says, let f and g be two functions such that f of g of x is equal to x for every x in the domain of g. So g of x will likely be different from x. You plug that different value into the function f, and it undoes whatever g did, and it takes you back to the inside value of x. Similarly, I could say, well, g of f of x must also be x. So you're going to plug x into f, and whatever that value is, you're going to plug into the function g. G is going to undo the actions of f and take you back to x. So the function g is the inverse of function f and is denoted as f inverse of x. And we can say any function composed with its inverse is just going to give you back the original domain x. And similarly, I could say, well, any inverse composed with the original function also is just going to be x, because again, whatever f does to x, the inverse will undo and take you back to x. Now, when we look at an example of a problem here where I'm just asking you, please show me that these two functions f and g are inverses of one another. Pretty easy. You can say, well, in order to show that they're inverses, I should be able to plug the second function into the first function and get an x. And similarly, I should be able to plug the first function f of x into the place of x in your second function, and it should simplify to be just x. So notice here, f of g of x, well, that's going to be f of g of x is the x plus 7 over 4. If I replace x plus 7 over 4, everywhere there's an x with an f of x, I get 4 times that group, x plus 7 over 4 minus 7. We know this 4 and this 4 is just going to cancel, so I'll have x plus 7 minus 7, which is just going to give us x. So that verified that f of g of x is x. Now what about the reverse order? What about g of f of x? Well, if I plug f of x, the group 4x minus 7, into the place of x within g of x, I'll say, well, that's just going to be g of 4x minus 7, which gives me 4x minus 7 plus 7 over 4. Well, clearly 4x minus 7 plus 7 is just 4x, and 4x over 4 simplifies to be x. So no matter what order we did the composition in, f composed with g of x is x, g composed with f of x is x. So it gives you back what you started with either way. That's conclusive evidence that these two functions are inverses of one another. Now, the process of finding an inverse. The equation for the inverse of a function f can be found using these steps. Usually, in fact, I think in all of the problems in the homework, they always start off with f of x for the original function. We know f of x is the same thing as y, so that'll be our first trivial step. Just replace the f of x in the problem with a y. And then what does an inverse do? An inverse is going to undo whatever the original function does. The original function is going to take each x value and assign a y value. Well, the inverse then must do the opposite and assign that y value back to x. So that's, in order to solve for the inverse, that's precisely what you do. I've had so many students say, oh, I don't understand why you have to switch the x and the y. I'm like, because that's what an inverse does. All inverse functions switch the ordered pairs. So you say, okay, I'll do that in my equation. I flip the x and the y values, and I solve for the new y value. Now that new y value is going to be the solution for your inverse as long as it is a function. It can't be anything like y is equal to both the positive and negative root, because that's not a function. It would have to pass the vertical line test. So as long as when you solve for y, you get a function remaining, then it's going to be okay. Now, if f has an inverse function, we'll replace y in step 3 by f inverse of x. We can verify our result by showing that either f composed with its inverse of x is x, and f inverse of f of x is x. I think in several of your homework problems, they'll ask you to do this. You can do either one. Just to save time in the homework problems, I only ever did this one right here. The function composed with its inverse of x is equal to x. I had to show that in each problem to verify that my answer was correct. Now, for the next part here, let's go ahead and find the inverse to this simplistic linear function. So you say, well, all right, we're given the original f of x is equal to 2x plus 7. Well, replace f of x with y. So then y is equal to 2x plus 7. The next step, you switch those x and y values. So you say, well, now your new equation is x is equal to 2y plus 7. The inverse function should be, when you solve this switched equation of x and y, in for the new y variable. So you say, well, if I'm trying to isolate that y, the first step I would do is subtract 7 on them both sides. I'll get x minus 7 is equal to 2y. That's what I did right here. And then let's divide by 2 on both sides. When I divide by 2, I'm going to get y is equal to x minus 7 over 2. Now, that is a function solved for y. It's not y is equal to the positive and negative of anything. It's y is equal to a function, one function of x. So this is fine. So then I can say, well, then I can replace that y with f inverse of x and say my inverse in this scenario is x minus 7 over 2. Glorious. Now, if you're thinking, well, that was a little straightforward, it was. Some of the homework problems do get more fun than that, but the only challenge is the algebra sometimes. And please just follow my work in the homework for that if you struggle with anything, or let me know. For the next one here, we're looking at how the horizontal line test is going to show you that an inverse exists. Remember, whenever we flip the x and y values, the new function that's supposed to be the inverse has to be a function, so it must pass the vertical line test. Well, if you flip the x and y values and the new function has to pass the vertical line test, then the original function must pass both the vertical and the horizontal line test, because if it fails the horizontal line test, then the inverse is not going to be a function because it would fail the vertical line test. That's all this is saying. A function f has an inverse if there is no horizontal line that intersects the graph of f at more than one point. So these are very, very, very straightforward problems. If I ask you to apply the horizontal line test, you'll have examples like the following. A, the absolute value of x is not a function that I can take the inverse of. Why? Well, because it's not one-to-one. One-to-one means that for every x value, there is one y value, and for every y value, there is one x value. That's not the case here. At y equals 1, the x value could be 1 or negative 1. So then when you flip those ordered pairs around, your absolute value function would look like this. When x is equal to 1, the y value would be 1 or negative. That's not a function. So you'd say, okay, I can't take the inverse of it. Now, in some of the problems, you'll see where they go through and they say, well, we can still invert it if we do a domain restriction. And they might say, well, how about we restrict this to go from 0 to infinity or negative infinity to 0? And in either of those cases, you could take the inverse of that portion of the absolute value function. But if I just give you a graph like this and say, can I take the inverse of it? No, because the inverse would not be a function. It fails the horizontal line test. Now, if I have something like this is the graph of an exponential function, its inverse would clearly be also a function because it passes the horizontal line test for all x and y values. Now, if I ask you to actually graph out an inverse, then all that we need to know is that the graph of the inverse of a function is the reflection about the graph of the original function about the line y equals x. And again, that has to do with because the only thing an inverse is doing is inverting all of those ordered pairs. Any x, y value becomes the ordered pair y, x on its inverse. Let's see that as an example here. You're going to have problems in your homework where you're given some original function that's just a collection of ordered pairs connected, and you're asked to find the inverse. Well, if I have this function here, y equals f of x, all I need to do is really concentrate on its ordered pairs. It's going to have the ordered pair -3, -2. So -3, -2 is an ordered pair on the original function. So it's going to assign an x value of -3 to a y value of -2. Well, I know the inverse better have the ordered pair -2, -3 then. Please notice, -2, -3 is a point on the inverse function. Now, the original function had the ordered pair -2, 2. Well, then its inverse better have the ordered pair 2, -2. I go to x equals 2, y equals -2, plot out that point. So the inverse of this line segment here is the line segment down here. Now, what about this one right here? I've already got that point plotted. What about this point? Well, this point on the original graph is the ordered pair 4, 1. Well, if the ordered pair 4, 1 is a point on the original graph, its inverse must undo that. It's going to have the ordered pair 1, 4. 1, 4, inverse point right there. I would connect those dots just like these are connected here. The inverse of this line segment is this line segment right here. Now, when you look at these two graphs disconnected, it's kind of hard to see that one is a reflection of the other about the line y equals x, which is why I generated this next screen. Boom. And you can see it pretty nicely. Here's our original function with those ordered pairs. These are the inverse ordered pairs of all of those connected out. And we can see then if we draw the line through the origin with a slope of 1 for y equals x, you can see how, yeah, this is just a reflection about that line. This part is a reflection about that part. This part here is reflected about and becomes this part. As one part moves further away from the line y equals x, so does its reflection. And so now I can say, well, yeah, that's a pretty cool problem. All right, guys, that pretty much does it for the introduction for this section. Please do try the work and let me know if you have any questions.